this presentation is called Python as a Hackable Language for Interactive Data Science. And my name is Steven, and I'm very excited to be here. Thanks to all of the NumFocus hosts for organizing this event. It's really a privilege. So with that, let's go ahead and get started. So just a little bit about me. I'm an engineer at Databricks based in the Seattle area. I don't know if my camera is still visible, though. If it is, you might see some palm trees in the background. That's because right now I'm in the beautiful island of Kauai on vacation. So that's a great benefit of a global conference. You can do it from anywhere. And if you hear a rooster in the background, don't worry, it's just a rooster. Nothing too crazy is going on. One of my big passions is computational notebook technology. You'll probably see a lot more of that as we go through this presentation. And when I'm not working on open source projects, I enjoy helping my wife out in our garden. And unfortunately, our cat has recently figured out how to escape from the garden. It's normally enclosed, but when there's a will, there's a way. So we have to figure out how to cat-proof it once we get back. So let's talk a little bit about who this presentation is for. So there's really two groups of folks, and those are tool users, so people who use Python to do some kind of data analysis, as well as people who want to implement tools for data analysis using Python. And I hope that if you're in the latter category, you might come away from this presentation with some ideas, maybe some crazy ones, perhaps, for ways we can improve people doing the lives of folks doing interactive data analysis. The only knowledge, however, that I'm going to assume is a very basic knowledge of Python or Jupyter. So with that, let's talk a little bit about why is Python so good for data science? Like, why has it kind of, I mean, there's definitely other alternatives, but generally speaking, Python has really dominated the data science scene. And I think, and this is just my opinion, but I think it comes down to two answers. The first is, of course, the ecosystem of data adjacent libraries. There's so many different libraries to do almost anything you could possibly want. And secondly, which I think is a little more subtle, is that it has really great tooling for interactive programming. So data analysis in particular is something that really benefits from interactivity, because a lot of times when you're writing a program to do some data analysis, you don't necessarily know what is the code that you want to write until after you see some preliminary results. So being able to iterate kind of in that interactive fashion is why tools like IPython and Jupyter and other tools like Spider, VS Code notebooks, and you may have seen Marimo, which is like the new hotness, have just been so useful for that. And so in this presentation, I'm going to focus on Jupyter in particular, and ways we can kind of augment Jupyter to do some kind of outside the box optimizations for your data analysis workflow. So one underappreciated aspect of Python towards this end is its extensibility. So let me just give the simplest possible example of one way in which Python is kind of extensible and how that has kind of benefited users of interactive tools like Jupyter. The simplest example, I think, is the top level await in IPython. So here we have, an async function. And normally you can't call this function directly, but here, because we're in Jupyter, I can actually run this like so with the top level await. And this normally isn't allowed. Normally you're not allowed to call await outside of an async function, but Jupyter has, or IPython actually has a transformer, an AST transformer, which essentially rewrites the above call into something that's a lot less convenient, but more correct from a Pythonic standpoint, where it's getting in an event loop and running the async function until it's complete. Definitely a lot less convenient though. So let's talk a little bit about abstract syntax tree transformations. So the top level await is one example of an AST transformation. And it turns out that Python exposes an API for these AST transformers via AST visitors. So what are some of the interactive features we can enable if we leverage these to their full extent? Like if we just take this to its logical conclusion, what can we do? So let's take a look at some examples. And I'll just say, as we're going through this presentation, all of these examples leverage an instrumentation library called Piccolo. And if you'd like to follow along yourself, they run within a special alternative to the IPy kernel called IPyFlow. And IPyFlow exposes a hook to kind of hook into Piccolo functionality. And this presentation, you probably notice, is just a notebook. So if you would like to actually follow along with these examples yourself, you can download it at the link github.com/ipyflow/PyData Global 2023. And you can always come back later after the presentation as well if you want to try it out. This isn't going anywhere. So let's look at our first example called optional chaining. So this is inspired from a recent flavors of JavaScript, which actually have this great syntax for what's called optional chaining or maybe monads, where you can say, hey, if I don't know whether some variable is null or not, I can prefix it with a question mark before I do a dot. And then that way, even if it's null, we can kind of coalesce subsequent things into a null value without a bunch of if-else statements to check everything. So we can actually add this to Python, it turns out. So let's see how. So first, I'm just going to run this snippet here, which basically registers the instrumentation or AST transformation that enables this functionality. Then I will go ahead and run something. We're just going to get, a simple class that kind of has an attribute that we can, one that has a value and one that will be null, which will be important later. So let's go ahead and see how this works. Of course, if I can do foo, now I can do foo .foo, and of course this evaluates to 42. But I can also, evaluate the null attribute, and I can try to get an attribute on the null attribute. But when I prefix it with this question mark, we can see that it kind of coalesces to none. And this works for even more complicated chains of attributes, or I can coalesce them into none with this kind of question mark syntax. Okay, so hopefully this whets your appetite a little bit with kind of some of the ways we can actually extend Python to make it maybe more convenient for certain use cases. But we're just getting started. So let's go on to the next example. And this is one of my favorite examples. For this example, we're actually going to make all assignment statements to simple variables non-blocking so that it appears as if they run instantaneously. So that's the idea. We're going to try and make all variable assignment appear instantaneous. And then we'll only block execution if a variable is used in a load context. So if a variable we assigned to is used in a load context, that's when we'll actually start blocking and waiting for the evaluation to finish. That is, we can actually get away with also making it appear instantaneous if the load context is itself part of a variable assignment. So this probably looked a little bit abstract. Let's see what this looks like in practice. So I'm going to do the same thing before, where I register the instrumentation to make this example work. So I'll just go ahead and run this code snippet here. Okay, and for this particular example, we're going to simulate some expensive computation with this function expensive, which sleeps for 3 seconds before it returns the value that was passed to it. Okay, so let's go ahead and run this code snippet where we assign x, we assign expensive of 1 to x. And as you can see, it appears to have run instantaneously, and that's because of our instrumentation we ran. And now let's go ahead and run this and assign x plus 10 to y. This also appears to run instantaneous because even though we used x in a load context, we were doing just another simple variable assignment. So we can keep track of all of the dependencies and figure out when it's okay to avoid blocking. Let's go ahead and make another expensive call here. This again appears to be instantaneous. And I think I've probably been talking for about 3 seconds. If you consider that to be think time, it appears as if this entire chain has been instantaneous. So if I actually run this quickly, you can see it block. So I'll go ahead and run maybe, whoops. Let's try getting back here. Maybe try running from here. I'll go ahead and run this, and then run this, and then run this. And you can see this time it actually blocked because I ran it quickly enough that kind of my think time was no longer leveraged because there wasn't enough time to wait for the execution to finish in the background. But you can imagine if you're doing something with really large data frames and you kind of know what computation you want to do and you want to start running it without waiting for intermediate results to complete, you can imagine that this might be a very convenient bit of functionality to have access to. Okay, but this is all child's play compared to the big one, which is reactive execution. So let's talk about reactive execution. So you may have heard of the state problem or out of order execution. It's a very well documented problem in notebooks. There's a great presentation from JupyterCon 2018, I think, by Joel Gruss called I Don't Like Notebooks, which talks about this issue in a lot of detail. It's an amazing presentation. Highly recommend you check it out if you haven't seen it before. I Don't Like Notebooks, Joel Gruss, JupyterCon 2018. And the reason for this is that the reason for some of these problems with notebooks is that you can kind of run things out of order and it gets really hard to keep track of the state of the notebook because you have to think about it in your head the whole time. So one partial solution to this problem is to reactively rerun dependent cells whenever something changes. So let's take a look at what that looks like in practice. So once again, I'm going to get rid of the previous instrumentation and register some new instrumentation that permits this reactive execution. Let's go ahead and do that. And let's do some simple code here, x equals 0. We could do y equals x plus 1. And just to like spice it up a bit, we'll throw a print statement in there, something that doesn't have any dependencies on the previous things. And then we'll just print y. So with the IPyFlow kernel, which is what this is running on, the way this works is when I have a particular cell selected, anything that has a dot next to it has a dataflow relationship with the selected cell. So in this case, y has a dataflow relationship with this cell y equals x plus 1, as well as this cell x equals 0. And in particular, you may have noticed some of these dots are purple, this dot is orange. What does that mean? Well, anything with an orange dot will also execute when the selected cell executes. So for example, if I come up here and select x, whoops. If I come up here and select x equals 0, you can see cells 23, 24, and 26 all have orange dots. If I select y equals x plus 1, cell 24 and 26 have orange dots. Let's actually try running something in here. So I'll change this to x equals 42, run this, and you can see, indeed, all of the orange cells reran. And I could come here, change this to something else, and once again, the things that had orange dots next to them reran. And the important thing here is, of course, the thing that wasn't related to these cells at all, this print statement, was totally skipped. So if this is like some expensive computation that's not necessary, it'll totally get skipped. And it won't have, or if it has side effects, it'll also get skipped. So this is the basic idea of reactive execution. Basically, automatically refresh anything that has maybe gotten out of sync, so that the kind of top to bottom visual presentation of the notebook is exactly in sync with the state of the notebook. Kind of what you see is what you get. And I'll also note that reactive execution is great for interactive widgets. So let's take a look at how we can use reactive execution with interactive widgets. So here I have a cell. I'm just getting kind of some x's along an x-axis. And then here's a cell to create a slider. We'll see how we'll use this later on. This will be our widget that we're gonna kind of use to interact with our plot. Here's our plot. And you can see what we're essentially doing is we're plotting cosine, and the period is kind of set by our slider value. So the higher that we put our slider value, the higher the frequency of this plot. And so here's the slider. And with reactive execution, I can toggle this. And you can see I just increased the frequency of the plot. I can increase it even more if I want. I can move it back down again. And so this is kind of like a great educational tool, being able to change sliders and have actually different cells depend on the slider value. And this will work for other kinds of widgets as well, but sliders are probably the best example to illustrate how useful reactivity can be. So I should probably move on with the presentation and not get too distracted, but it really is fun to play around with. So you might be wondering, though, why do we actually need AST transformations or instrumentation to enable reactivity? Like, couldn't we just kind of statically analyze the code to figure out when something needs to rerun? And for easy cases, it's true that static analysis does suffice. But in general, once you get to some of the corner cases, it gets really, really difficult to figure out what actually changed in order to reactively rerun something. So let's look at an example of this. So let's look at one of the harder cases. So here I have, I'm just setting some variables in this cell here. So let's run that. And then I'll go ahead and reference the first value x as well as the second value y. Now let's take a look at this second cell here. What do we think happens when I run this? Well, one of two things is going to happen. Either we're going to increment x or we're going to increment y. And we don't actually know which one is going to increment until we run this. So when you think about it, it's actually impossible to figure out what is the correct reactive execution for this particular example if we don't have some kind of instrumentation that actually allows us to observe the values as they change. And just to show you that this works, I'll go ahead and run this. And in this case, it looks like y was the thing that got incremented, because you can see that's the one that reran down here. So you might say, okay, well, this is kind of a contrived example. But when you think about it, anything that needs some kind of runtime introspection really needs these kinds of AST transformations or instrumentation in order to figure out what actually changed. So let's look at another example. This example uses what's called memoization. So what we're going to do is we're going to try and skip code that would give the same result if we've already seen it before. So once again, let's go ahead with our setup. Going to import time. And here we're going to simulate another slow method in a class called foo. basically, it's just going to return some constant, but it's going to sleep for 2 seconds before doing that. Okay, so now we're going to get an instance of foo shoved into a dictionary. So we'll go ahead and run that. And down here, we'll go ahead and run this particular cell, which will actually call our slow method and then show the result. Okay, so far so good. Now, if I rerun this top cell here, you can see it's the exact same code. So theoretically, we shouldn't have to actually re-execute our slow stuff. We can just get the memoized version and it'll be fast. And that's exactly what happens when I do that. And this is only possible because we can actually see the code and we can see the runtime values and tell that they haven't changed. If they do change, so let's go ahead and change this to something else. This time, you can see that it actually is slow again. It took some time. But if I change it back to something that it's seen before, it's fast. And if I change this back to something that it's seen before, fast again. And let's change it to something it hasn't seen. It's slow, taking a couple of seconds. And if I change it back to something that it's seen, fast again. So in order for this to work, you really have to know what's executed previously. You have to know if the runtime values match up with something that you've seen before. And so this is another case where it's really beneficial to have instrumentation so you can actually see what changed. So you might be wondering, how does all of this work? Well, I mentioned we're using AST transformers, but it's actually really hard to get all of these examples to work with traditional AST transformers because usually we need to register a bunch of different ones. And they tend to kind of conflict with each other. They don't compose very well. So to give you an example of what I'm talking about, let's say I want to, rewrite all binary operations with a plus to add a new binary operation. Well, if I'm doing this multiple times, it's kind of explode and cause, and they'll conflict with each other. So to combat this, these examples all use a library called Piccolo. And what Piccolo allows you to do is it allows you to have composable AST transformations. So I can register multiple transformers in a way that they won't actually kind of conflict with each other. So let's just take a quick example. So this particular transformer, what is it doing? Well, when we see the right side of a binary operation, it's just going to increment it. So if I actually register the instrumentation for that, and then I run 2 plus 2, you can see we get 5. Now, what if I want to register another transformer that increments the right binary operation by 2? Well, if I were using a traditional AST transformer, this 2 plus 2 would have gotten rewritten to 2 plus 2 plus 1. And then both of these, 2 plus 2 as well as 2 plus 1, would have gotten rewritten to be incremented by 2. And so it would actually end up incrementing this by 4 if I go ahead and register this, if I were using a traditional AST transformer. But with Piccolo, they compose. So I can go ahead and run this. And this time I'll get, I think, 7, right? And 2 plus 2 plus 1 plus 2. I'll get 7 instead of 9 because these will compose nicely and don't kind of conflict with each other. So in conclusion, Python is actually surprisingly hackable, and its hackability enables all kinds of really interesting interactive use cases. And if you'd like to play around with some of these examples yourself, you can go to the GitHub repo, ipyflow/PyData Global 2023, or you can check out the examples in the Piccolo repository directly, and that's at github.com/smacky/piccolo. Um, so with that, thank you very much for your attention. And I think I have a few minutes left to open it to questions if there are any. Really appreciate your attention. And I was not able to see anything at all while presenting, so my apologies if there were questions